Okay, so what we have so far? So far we have that if we have, in the theorem 5.9, last time we showed if we have this series fn of z minus 1 converges absolutely and uniformly. Wow. Absolutely and uniformly over complex subsets of a region G. If this condition is satisfied, then the infinite product Fn of z converges in the H of G. H of G means the set of all analytic functions in G. Okay, so that's very good. Okay, so we're going to use this condition to solve our original problem. What is our origin problem? We have a sequence of an in G, in region G. It has no limit point, with no limit point. In G, it may have limit point on the boundary of G, but it has no limit point inside G. And if we want to ignore the multiplicity, we don't want to mention the multiplicity here, this sequence of an may contain finitely repeated points. Maybe like A1, like A1 up to A10, they represent the same element, and A11 up to A20, they represent A11 to A100, they represent another same point. But you can only have finitely repeated point. This will help us to ignore that multiplicity. The repeated is a multiplicity, right? Okay, so we want to construct an analytic function with an as zeros and the number of the repeated times as a multiplicity, right? That's our original question. Of course, we may consider consider the infinite product z minus an. We want this infinite product to converge to some function. Well, based on our idea, we need this. So we need this sigma. This is Fn. This is Fn. This is going to be Fn. So sigma Fn minus 1 converge. Well, clearly this series does not converge, right? So it does not converge. Then what's going on? What can we do? We need this z minus an, but it does not solo work. It does not solo work. So what we are going to do is the following. We multiply it with some another analytic function, g sub n of z, gn of z. Okay, with this factor, we want this series converge uniformly and absolutely. And of course, we need what? We need this g sub n of z not contributing additional zeros. Okay, we don't want any other zeros from gn of z. because you are going to multiply z minus an by this g sub n of z. So this function is only used to make this series converge, but it does not contribute additional zeros. Okay, so we want g sub n of z help to make it convergent. And Gn of z analytic, of course it has to be analytic and non-vanishing. Okay, so it'll work, it does not give us trouble. All right. Non-vanishing, the easiest way to make an analytic function non-vanishing is that it is a common choice to have g sub n of z as the exponential of h sub n of z. Exponential function with the analytic function h n of z is analytic, and the exponential function will give you non-vanishing property with h n of z analytic. Okay, so this is always a first choice, the first choice. When you need analytic and non-vanishing, you just use exponential function. Exponential function will make whatever analytic function non-vanishing. Right? And also we know that if G is simply connected, analytic and non-vanishing function are of this form, because over the simply connected region, the logarithmic function is always well defined. The branch is well defined. So even though we consider this as a first choice, actually over certain region it's a unique choice. Okay, so that's the strategy we have. We still want z minus an. We still want z minus n, but z minus n itself does not give us a convergent series like z minus a and minus 1, like this one, f sub n of z minus 1. It does not converge. It does not converge, so we multiply it by some factor, analytic factor, g sub n of z, so that this series converge. If such gn of z exists, we make it converge. Well, at the same moment, this g sub n of z cannot give you additional 0. So g sub n of z should be analytic and non-vanishing. Analytic is okay, but non-vanishing, how can we guarantee a function is non-vanishing? We use exponential function. Exponential of analytic function is always analytic and non-vanishing. So that's the idea. And also we say that even though this is one choice, but for the simply connected region, this one choice is actually the unique choice. Okay, so we don't lose the generality over this region. Over this region, we don't lose the generality. All right. Okay, so let's see how do we construct such Gn of z. In this section, it's called a Weierstrass factorization. Is it right? I think it's yes, that's called a Weierstrass factorization theorem. It's because of this g sub n of z is constructed by Weierstrass. Okay, okay. Now let's see the construction. Let's start from the definition. 510 definition. An elementary factor elementary factor is one of the following functions: EP of z, EP of z for p equal to 0, 1, 2, and so on. So E0 of z is 1 minus z. E0 of z is just 1 minus z. EP of z is 1 minus z, and the exponential z plus z squared over 2 plus z to p's power over p. Here p is greater than or equal to 1. Okay, so this is the elementary factor. Elementary factor. Okay, the elementary factor, let's check the function. EPZ over P. First of all, EPZ, this function has just unique 0, 1. When z is equal to 1, it is equal to 0. This, from here you get a 0. This exponential function does not give you 0. Sorry, not P, A. By rescale this z, we know that EPZ over A has a simple 0 at z equal to A. Okay, so you just divide it by A, you will get, you rescale it, you rescale A to be, 1 to be A, and no other, just one simple 0 at A and no other 0. Okay, so that's very simple. And also, if B is inside C but without G, outside of G, even the boundary point is okay. If B is outside of G, then it's E P A minus B, Z minus B. Because it's outside of G, so Z is not equal to B, so this is well defined. And this one, when Z is equal to A, it is also a 0, because when Z is equal to A, you get a 1. We just make this part a 1. So this one has a simple 0 at Z equal to A, and it is analytic. Inside G. It's analytic inside G. Okay? Okay, so we are going to use this elementary factor to construct the required function, analytic functions. But before that, we have to verify certain properties. We have to guarantee that infinite series converge so that the corresponding product converge to an analytic function. Okay, so the first property is that if we have this z small, modulus is less than or equal to 1, and this p is greater than or equal to 0, then 1 minus EPZ is less than or equal to z to power p plus 1. z to power p plus 1 is controlled by the z to power p plus 1. Okay. Of course, here p is greater than or equal to 0. Okay, so if p is equal to 0, the E0 of z is just 1 minus z. So 1 minus E0 of z is equal to z. Equal to z, then you put the up's value is less than or equal to up's value of 0 plus 1. P is equal to 0, so 0 plus. That's the same thing. Okay? It's trivial. So that's why it say, the author says we may restrict our attention to the case p is greater or equal to 1. Because the first case is identity, not the inequality. Okay, so we'll assume this p is greater or equal to 1. We fix this p, then EP of z is an analytic function. Analytic function can have its power series representation. So we have this power series expansion about z equal to 0 is its power series expansion about x equal to 0. X equal to 0. A sub k, yeah. Then we are going to differentiate two sides. We differentiate these two sides, we get the EP prime of z. The first term disappears, okay? And here you will get sigma k from 1 to infinity, k a k z to k minus 1. Power series has such property. We can do the term by term differentiation. And this is a differentiation about power series. We can also do the differentiation about this one. We have a concrete expression. It's a product rule, right? So you will get EP prime of z by the product rule. Differentiate first term, you get a negative exponential of z plus exponential of this. And then plus 1 minus z exponential and times the derivative internal stuff. Okay, the derivative internal stuff is 1 plus z plus z to power p minus 1. Remember, here you differentiate z to p. It's a p times z to p minus 1. P canceled. You always cancel the base. All right, that's the purpose of this construction. And then 1 minus z times this. Continue. Exponential, we have exponential. All places have exponential. Then here you have negative 1. This product will give us 1 minus z to power p, z to p's power. Z to p's power. Right? So 1 minus z, 1 plus z squared z to p minus 1 is this. And negative 1 comes from this negative sign. Then you cancel negative 1 with positive 1. You get a negative z to p exponential z plus z to p to over p. Okay, so that's how. That's what it is. And we compare those two formulas. If we compare those two formulas, we will see what? This one, this power series expansion has a minimum power z to p's power. And here it starts from k equal to 1, so it's a a1, just a1. K equal to 1, yeah, just a1. And a2, z. a3, z squared, blah, blah, blah. Right? Yeah, so if you compare those two expressions, we will have that a1 is equal to a2 is equal to a3 is equal to, you see, here you will have PAP z to p minus 1. PAP z to p minus 1 and continue. Well, this has power p minus 1. All the coefficients are 0. All the coefficients are 0. Okay, and the second thing, what is the expansion of an exponential function? The power series expansion for the exponential function is x to n factorial n from 0 to infinity. So all the coefficients are positive. or positive coefficient. And together with this the polynomial, this polynomial also has a positive coefficient. So the xp z plus z to p's power over p has all positive coefficients, right? It has all positive coefficients. And with this negative sign, it means this Taylor series has all non-positive coefficient. So AK here. All the AKs will be negative for k is greater than or equal to p plus 1. Right? All the AK will be negative because we have the negative sign. Then it means upper value of AK is equal to negative AK for k is greater than or equal to p plus 1. That's the place you get p plus 1. Okay, so now let's do the evaluation. You let EP1, remember EP1 is 0. EP1 is 0. Where's EP? EP is here. Yeah, EP is no, EP is here. EP is here. So you let Z be 1, so you will have 1 plus what? 1 plus sigma. You let Z be 1, k from 1 to infinity, AK. Just k from 1 to infinity, AK. Right? So if you move this term to the left side, you will get sigma k from 1 to infinity negative AK. Right? You move everything to the left side. Is equal to 1. This negative, remember this negative is upper value. Upper value of AK. So this place we use a property. We use this property. We use here's p plus 1. K is from p plus 1. The rest of them will be 0. Here, let's say p plus 1. P plus 1. Okay. Okay, so now let's prove it. For z modulus less than or equal to 1, EP of z minus 1 is this, right? We have the power series expansion minus 1, you remove this 1 and you only have a power part. Z to n's k's power. AK is always 0 up to AP. Where do I put it? AP. So you start from K starts from P plus 1 to infinity, AK Z to K. And then we're going to apply the triangle inequality. And remember the minimum power is P plus 1. So right, you factor out the Z to power P plus 1. And then the triangle inequality. And remember this one is less than or equal to 1. And this is equal to 1. So we have it. We have this upper value of difference is less than or equal to z to the power p plus 1. Upper value of z to the power p plus 1. All right? So it's a very delicate construction, the proof. It's very good. You should be able to reproduce it. Okay? Okay, very good. So now let's prove the theorem. Now let's prove the theorem. Okay. Now let's see this special case of the theorem. The special case of theorem means we are going to choose G equal to C, the complex plane, all complex plane, and try to prove it. Let AN be a sequence in C. Such that the limit of the upper value of AN is infinity, and AN is not equal to 0 for all n greater than or equal to 1. So we don't want 0. If we want 0, we multiply it by z. That's enough. So we don't lose the generality. So here we emphasize this is not a sequence of distinct points. But by hypothesis, what hypothesis? The limit is infinite. The limit of upper value of AN is infinite. By hypothesis, no point is repeated an infinite number of times. An infinite number of times. Okay, so by this condition, we don't have to mention the multiplicity. You can just use repeated AN to cover the multiplicity. If Pn is any sequence of integers such that series 1 over upper value of AN to power Pn plus 1 converges. So if this geometric series, or not the geometric series, the power series converges for all r greater than 0, then if this power series always converges for r greater than 0, once one such sequence of an integer exists, then the function fz as the infinite product n from 1 to infinity E sub Pn of z over a sub n converges in H of C. Okay, so we have this analytic function converging to this analytic function, and the function f is an entire function with zeros only at the points an. If z0 occurs in the sequence an exactly m times, then f has a 0 at z equal to z0 of multiplicity m. Up here m times, the multiplicity is m. So that's what I said. The multiplicity is recovered by the by this condition. Okay, so another thing, if there's such integer, then you have it. Well, will this kind of a sequence always exist or not? Okay, so if such Pn does not exist, then what will happen, right? So furthermore, if P sub n equal to n minus 1, then this condition is called 5 what's the number? 5.13. This condition is called 5.13. 5.13 is satisfied, will be satisfied. So it says actually, even this simple choice will guarantee the condition. Will guarantee the condition. So you don't worry about it. You don't have to worry about it. And this place, you see this place, a sub n is not equal to 0. Why we have such restriction? Because we are going to put it on the denominator. And we don't lose it. As I mentioned, if you have 0 as a 0, you just multiply this by z to a certain power. We don't mind to remove finitely many points. We cannot handle infinitely many points naturally. We have to have some theory to guarantee the infinite product, but finite product is not the problem. Okay, so this does not lose the generality, but it is required in the computation. And the furthermore part just guarantee the existence of such Pn. Okay. Okay, so let's see the proof. This is very long, and it's a case when G is equal to C. And C, its boundary is infinity, so you must push this an to infinity. If it is bounded, if this an is bounded, then it definitely has a convergent subsequence. It will have a limit point. That's wrong, right? Okay, let's see the proof. We'll assume this. Suppose Pn exists and satisfy 5.13. Satisfy that's 5.13. Then by lemma 5.11, what is lemma 5.11 here? This one, lemma 5.11. By lemma 5.11, let me. We have ops value 1 minus e p sub n z over a sub n is going to be less than or equal to z over a sub n p sub n plus 1. And here, okay, this is a condition, but be careful, this place will require z over a sub n is less than or equal to 1. Z over a sub n is less than or equal to 1. For each an, we have such thing, right? For each an, we have such thing. So This is the condition. If. So now we fix some r greater than 0. Fix r greater than 0. Fix r greater than 0. Remember that this an has ups value limit of ups value infinity. So there is and capital N in the natural numbers such that for all n greater than or equal to capital N, ups value of an is strictly greater than or equal to r, greater than or equal to r. Okay, then for z less than or equal to r, of course it will be less than or equal to a sub n. This condition guarantees this. We have one minus e p sub n z over a n ups value less than or equal to z over a n p sub n and less than or equal to p sub n plus 1 is r over ups value of a n to power p sub n plus 1. Okay, so we have such thing. We added this condition, and this condition is uniform for n sufficiently large. Okay, so we get this. It is dominated by a convergent series. Remember, we assume it's correct. This is just true for n greater than or equal to capital N. So we start from capital N, but still it is convergent. It's dominated by this convergent series on the disk. On this closed disk, it's compact set. It's compact set. So this implies that the series and from 1 to infinity 1 minus e p n of z over a n converges absolutely. Okay, converges absolutely, and because it's compact, uniformly. In the h of g. If it converges absolutely and uniformly, then by the product, by the 5.10, remember the first theorem we mentioned. No, here 5.9, the theorem we mentioned. Then by theorem 5.9, we have the infinite product e p sub n over z over a n, and from 1 to infinity converges in h of g, in h of g, h of c. G is c, this part, let's emphasize it's h of c. H of c. Okay. So that's good. That's good. If such Pn exists, then we can always do it. Each such Pn exists, we can always do it. And now we are going to show such sequence Pn really exists. So we show that such Pn exists. How do we show Pn exists? Well, it's not difficult. The limit of the ups value of an is infinity. Then there exists capital N in the natural numbers with n greater than or equal to capital N. Oh, for each, okay. This way, here. For each r greater than 0, yeah. For each r greater than 0, we have to fix r first. For each r greater than 0, there is a capital N in the natural number such that with n greater than or equal to capital N, ups value of an is greater than or equal to twice of r. Yes, greater than or equal to twice of r. Okay, so this n depends on r. Then r over ups value of an is less than or equal to 1/2 positive, less than or equal to 1/2 for n greater than or equal to capital N. And we know that right? We know that the series of 1/2 to power n from 1 to infinity converges. So the series r over ups value of an to power n converges. It's dominated by that. And then this place p sub n is n minus 1 because you use p sub n plus 1 is equal to n, so p sub n is n minus 1. Right? So that's our stuff. Okay, so very good. So we finished the proof of the special case when this G is equal to C. So here we just prove the existence of P sub n. Actually, if you choose some, you can also choose some large P sub n, right? P sub n can be as large as possible, and this is one of a possible choice of a P sub n. But remember that if you choose a bigger P sub n, then check here. If you choose bigger P sub n, then this expression will be more complex. Okay? So P sub n can be selected very large. But then EPZ will be very complex. It's not a complex number complex, will be very complicated. So we want P sub n as small as possible. Okay, so we just want a small P sub n. And this will depend on the growth rate of the limit of ups value of a sub n. Okay, and it may depend on the rate of the limit ups value of a sub n converges to infinity. If it converges to infinity very fast, like you choose 1, 10, 100, million, 1,000 stuff, possibly you will choose P sub n small, very small. If you let an as a 1, 2, 3, 4, 5, very tiny, then possibly you have to choose P sub n very large. Okay, so that's one of our observation. So next, we are going to show the Weierstrass theorem. Let's see the Weierstrass theorem. 5.14, the Weierstrass factorization theorem. Okay, so what is a Weierstrass factorization theorem? Remember that the previous proof is for the special case G is a whole complex plane. For the whole complex plane, function is analytic over the whole complex plane is called entire function. So let f be an entire function. And let a sub n be the non-zero zeros. Non-zero zeros of f repeated according to multiplicity. Okay, suppose f has a 0 at z equal to 0. This is a non-zero zero here. A 0, 0 of order m greater than 0. Okay, if at 0, the 0 with order 0, then it has no 0. Okay, so it's a bad. So that's why they also write it. A 0 of order m equal to 0 at z equal to 0. A solution of order m at 0. Don't use 0 because we're talking about number 0. A solution of order m equal to 0 at number 0 means f0 is not equal to 0. Okay, so that's why we don't put equals on here. Okay, then there is an entire function g and a sequence of integer p sub n such that f of z is equal to z to mth power. It's an order of a solution 0. Infinite product e p sub n of z over a sub n from 1 to infinity, and times exponential of g of z. Okay, so you can factor it. You can have the 0 part, the z part, the 0 part, and the non-zero part. Okay, so that's why it's called a factorization. So by the preceding theorem, okay, now let's prove it. This is exactly the formula of the preceding theorem. Okay, so by the preceding theorem, we have h of z equal to z to m. This one is not preceding term. This you just add it because you have finite product. This part is preceding term. Has this function, analytic function, has the same same zeros as f with the same multiplicity. Right? Same zero with the same multiplicities. Then this implies f over h has removable singularities. At 0, a1, a2, and so on. Okay? If you have removable singularities, you just consider them as a regular number. Then that's f over g is an entire function and non-vanishing. Entire function non-vanishing. Now we are going to use the property C is simply connected. If you have simply connected region, you can always define the natural log function. Then there is an entire function, another entire function, g, such that f over h is exponential of g. Well, this is exactly f is z to m infinite product ep sub n of z over a n from 1 to infinity, and the exponential of g. And we prove it, right? So that's a proof. Okay, so we finished the Weierstrass factorization theorem. Still a minute. Let's stop it here. Okay, very good. Thank you. We will continue in the next video.